Welcome back to The Explainer, everyone. Today, we're diving straight into something absolutely critical and honestly pretty intense. We are cracking open the functional safety checklist for hybrid dual-motor PCS systems. You know, the massive one with the 45 core faults across 5 dimensions? Yeah, that one. Specifically, we're zooming in on Category B inverter and power stage faults, and we're going right for the throat with subcategory B02, overcurrent and short circuit protection. When we talk about hitting ASIL D safety targets, we aren't just talking about writing clean software, right? We're talking about building an ultra-fast, multi-layered survival mechanism for the vehicle's actual power stage. So let's jump right into the physics of how these catastrophic hardware failures happen and the sheer engineering brilliance it takes to stop them. Okay, look at this number, 1390 amps. That is the sheer, terrifying scale of an uncontrolled demagnetization surge. I mean, we are talking about a massive tidal wave of current slamming into a system in literal microseconds. If your hardware and software aren't perfectly synced up to catch a surge like this, well, it's just going to completely punch right through your power component's safe operating area. It is without a doubt the ultimate destructive force in an EV inverter, and that's exactly why overcurrent protection isn't just some nice-to-have feature. It's literally the foundational bedrock of the entire powertrain.
So to tame this beast, we're going to follow a defense-in-depth roadmap today. We'll hit 5 key areas: fault root cause analysis, software and hardware code diagnostics, DFMEA key design prevention, PFMEA key process controls, and finally, DVPNR production validation. Let's get right into it.
Kicking things off with Section 1, Fault Root Cause Analysis. Let's take a look at the threat.
To defeat this kind of enemy, you really have to understand just how insanely fast it strikes. We're basically facing the 4 horsemen of the inverter apocalypse here. You see, modern silicon carbide, or SiC modules, are incredibly efficient, mostly because they switch extremely fast. We're talking over 10 kilovolts per microsecond. But that extreme speed breeds some unforgiving electromagnetic threats. First up, you've got the Miller effect, causing shoot-through. Second, high current change rates, or DIDT, interacting with parasitic inductance to create lethal overvoltage. Third is uncontrolled generation, or UCG overcurrent. This usually happens when the rotor angle suddenly jumps 90 to 180 degrees, maybe due to EMI or a weird sensor glitch. And fourth, high-frequency noise that actually tricks your DSAT protection into a false lock.
Let's actually zoom in on the exact mechanics of that first threat, shoot-through. Imagine the upper bridge arm switching on at lightning speed. That massive dV/T injects a huge displacement current right into the lower arm's parasitic millicapacitance. Now, if the gate driver can't clamp that voltage down fast enough, the lower gate accidentally triggers. Boom. Suddenly, both your upper and lower arms are wide open. You've just created a zero impedance path straight across the DC bus. The current spikes to thousands of amps instantly, and the resulting joule heat literally melts the silicon chip. It's game over in a fraction of a blink.
Moving on to Section 2, SW/HW Code Diagnostics, the Active Shield.
Now that we know exactly how fast this system can destroy itself, we obviously need a real-time defense. Basically, an electronic airbag. And the craziest part is this tiny window of time right here, 1 to 2 microseconds. That is absolute all the time your hardware has to detect a fault and react. Think about that for a second. If you wait around for the main software loop to see the problem, your inverter is already a puddle of melted metal. The hardware isolation driver and the overcurrent detection gating have to operate completely autonomously within this 1 to 2 microsecond window just to block the PWM and halt that energy transfer.
So how does the hardware actually pull off this safe? Well, it uses a brilliantly choreographed 3-step sequence that we call the 2-stage turnoff. Step 1, the isolation driver detects a sudden surge in the voltage drop across the transistor. Step 2, and honestly, this is the genius part, it doesn't just slam the gate shut. If it did that, the sudden stop in current would cause an inductive spike that would blow the system up anyway. Instead, it gently reduces the gate voltage. It forces the transistor into the state of weak conduction just to cap the peak current. And finally, Step 3. Once the current is contained safely, it completely shuts off.
Now, while the hardware is down in the trenches fighting that microsecond battle, the software is racing against a completely different clock, the fault-tolerant time interval, or FTTI. For ASIL D, this is strictly less than or equal to 60 milliseconds. The software is continuously running these complex diagnostics in the background, things like checking for Kirchhoff's current law residuals, basically making sure all phase currents sum up to 0. If it detects a leak, it locks the fault in 2 milliseconds flat. It's also monitoring for negative sequence currents and PI controller saturation, which it locks in at 1.1 milliseconds. Basically, the software acts as the commander, validating the split-second decisions made by the battlefield hardware.
Okay, so once a fault is actually confirmed, the system has to adapt its fallback state, and this depends entirely on how fast the car is moving. At low speeds, say under 20 kilometers an hour, the system safely executes an active open circuit, or AOC. It just shuts off the gates and lets the car safely coast, freewheeling to zero torque. Easy enough. But at high speeds, over 80 kilometers an hour, the motor's back EMF is massive. If you try to use AOC here, the motor acts as a giant uncontrolled generator and will absolutely nuke the inverter. So instead, it uses a stepwise active short circuit. It strategically shorts two phases for just 1.5 milliseconds to absorb the initial shock, and then it shorts all three lower phases. This successfully clamps the overvoltage to under 720 volts. It is super elegant.
Which brings us to Section 3, DFMEA Key Design Prevention. Let's look at the blueprint defenses.
So how do we guarantee these split-second defense systems are actually robust? Well, we engineer the physical threats right out of the system during the design phase. Look at this strict requirement, less than or equal to 15 nanohenries. To prevent those massive voltage spikes we were just talking about, engineers have to design the high-voltage laminated bus bars with this incredibly tight, symmetrical sandwich structure. By squashing the stray parasitic inductance down below 15 nanohenries, they ensure that even during a brutal short-circuit shutoff, the resulting voltage spike stays well within the silicon carbide safety limits. And the hardware specs, they are just as extreme. We're talking an active Miller clamp pulling down to -5 volts to absolutely physically prevent that shoot-through effect from happening. The driver chips themselves have to endure a common mode transient immunity of over 100 kilovolts per microsecond. Plus, we use ultra-stable Class 1 COG capacitors and highly precise 0.1% film resistors to prevent any thermal drift when under heavy loads. Oh, and on the software side, we embed a high-resolution 2D inductance lookup table to dynamically compensate for magnetic saturation. This makes absolutely sure the control angle never slips during a massive current surge.
All right, Section 4, PFMEA Key Process Controls. The Assembly Guard.
Here's the thing. A perfect blueprint means absolutely nothing if your manufacturing process introduces microscopic flaws, right? So, out on the factory floor, the line uses ruthless automated screening. Every single stator gets hit with a 2.5 kilovolt surge just to check for partial discharge. This detects even microscopic scratches in the wire insulation. We also use acoustic microscopes, or SAM, to scan the silver centering under the chips. If there is a void larger than 1%, the part is immediately scrapped to prevent local melting. Even the bolts are optically recognized and driven by servo tools that measure torque and angle to guarantee contact resistance stays below 5 milliohms. Literally, human error is completely engineered out of the assembly equation.
And finally, Section 5, DVP and R Production Validation. Let's step into the crucible.
Okay, we've got a flawless assembly. Now we enter the final battle. We take the physical unit and subject it to brutal, simulated destruction just to prove it holds up. In the Type 1 and 2 physical short circuit tests, we literally force a dead short while the system is running at 150 degrees Celsius and 800 volts. The acceptance criteria? Absolutely zero tolerance. The desat must trigger in 1 to 2 microseconds, and the voltage spike cannot exceed 1,000 volts. No exceptions. Then, in hardware in the loop, we spin a simulated motor up to 12,000 RPM and use an FPGA to inject a sudden 180-degree angle shift. The system has exactly 60 milliseconds to catch it and smoothly transition into that stepwise ASC fallback we discussed, keeping currents under 550 amps without demagnetizing the motor. Finally, we do the LV214 thermomechanical tests, which basically try to shake and bake the system apart just to ensure contact resistance and electrical balance hold perfectly steady.
Which brings us to our final thought for this explainer. I want you to look at your own designs. Are your DSET parameters truly optimized for these extreme overvoltage transients? Finding that perfect balance for your slow turn-off timing takes some incredibly complex calculations. But hey, fortunately, you don't have to guess. We can actually generate a dedicated dynamic Python simulation report to model your exact parasitic inductance and gate resistance. It gives your safety team the exact scientific foundation they need for a rock-solid safe operating area. So, I challenge you, apply this rigorous functional safety standard to your own EV hardware. Thanks so much for hanging out with me on this explainer, and as always, keep engineering the future.